All right, today we're going to look at similar triangles and polygons, section 12.4. So we first need to remind ourselves what is meant by similarity. Polygons or figures are similar when they have the same shape but are different sizes. So this will work with any polygon. Today we're going to primarily focus on triangles. So if we're looking at similar triangles, they need to have two things. Similar triangles have corresponding sides proportional, and corresponding angles congruent. So let's just recall from what we have done in the past, what do we mean by corresponding sides and corresponding angles? So if triangle ABC is similar, and the notation for similarity is just one curve. So I'm going to say ABC is similar to triangle DEF. Now, by just looking at the parts, take a look at the order. A, B, C, and D, E, F. Whichever one comes first corresponds to whichever one comes first. Whichever angle comes second corresponds to the second angle, etc. So we could say for corresponding sides, we can start with side AB is to side BC as, well, since we went A to B and then B to C, we would do the same order. DE is to EF. We can also say side BC is to AC as, well, since we went the second to the third, we need to do the same on the second triangle. E to F. And then since we went from angle A to angle C, we would need to do the same order and go angle D to angle F. But we can also write it another way. We can also say, well, I could go from A to C is as D to F as, and you can pick any of the other sides. Perhaps I say BC is to EF. And this can keep going for a lot of different combinations. The angles, however, are far less, there's far less options for the angles. So for the angles, we only have three angles, therefore we only have three combinations. We would say angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent, therefore, to angle F. Okay? So first of all, that's just a refresher in finding corresponding parts. The other I want to remind you of is how to solve proportions. Since we're talking about things being proportional, we need to remember how to solve when sides are proportional. So just as a refresher, proportions are equal ratios or fractions. So I could say A is to B as C is to D. And if you recall from earlier chapters, A and D are what we call the extremes, and B and C are what we call the means. So to solve, we can use a cross product. In other words, A times D, the extremes, is equal to the product of the means, B times C. So for example, if I give you 4 is to 7 as x is to 21, now you might just see that if I multiplied 7 times 3, I get 21. Therefore, 4 times 3 would give me 12. But if you don't happen to see that, we can always do cross products. I can say 7 times x is the same as 4 times 21. 7x is the same as 84. Divide both sides by 7. And I'm left with x equals 12, which is what we had interpreted and we had determined if we had simply multiplied straight across by 3. So that's just a refresher on similar triangles and proportions. Let's take a look at solving and simplifying some triangles that are similar. Okay. It's not as racing as easily as I thought it would, so I'll have to take care of that in just a moment. Let's take a look at some examples of similar triangles and how we can use them to determine a side length. So for example, I'm going to tell you that given triangle ABC is similar to triangle DEF. Now we just went through all the corresponding parts and corresponding angles. And I give you two pictures, not drawn to scale. Triangle ABC, where side AB is 4, side BC is 5, side AC is 8, angle B is 70 degrees, angle A is 80 degrees. Now if they're similar, make sure I go in the corresponding order. So D corresponds to A, E corresponds to B, F corresponds to angle C. Because they're similar, I know their corresponding angles are congruent. And at this point, I need one of the sides, so I'm going to give you that side DE is 8. And what I would like to do is determine what the side lengths must be on the other two corresponding sides. So you know me, I like to start with what I know first and identify what's already given. So in this case, let's see. In this case, I know DE and I know it corresponds to AB. So I know AB is the same as corresponds to DE. So I'm going to set up my other proportions. Since BC corresponds to EF, I will start there. BC corresponds to EF. AB is 4, DE is 8, BC is 5, and our question is, what is EF? Okay. So I can cross multiply. 8 times 5 is the same as 4 times side EF. Divide both sides by 4, and I get that EF equals 10. I can set up the same proportion because they're similar rather. So I can say the same thing. AB is this time to AC as 8, whoops, sorry, got a little ahead of myself, as DE is to DF. Filling in what we know, AB is 4, AC is 8, DE is 8, and we're looking for side DF. Now you can, whenever you notice, you can reduce a fraction to make the numbers easier to work with. So in this case, I'm going to go ahead and reduce this to a 1/2 is the same as 8 out of something. So again, some of you may just recognize DF is automatically going to be 16. But when in doubt, work it out. So I get 2 times 8 is the same as 1 times side DF. So DF equals 16. Okay. So hopefully that helps. Then we might also move into something that is a little bit more abstract. So I'm going to give you a second example. This time I'll make them right triangles, and I am going to tell you that triangle LNM is similar to triangle QSR we'll make LNM, whoops, LNM, LNM, with N being a right angle. And we will make Q, notice S has to be the right angle because it's in the middle, so it's in the corresponding place with N, and R. Ln is 5. This is x plus 4. Qs is 10. And this is 20. So we can do this logically. We can do this obviously using what we already know. Logically, you may see that since I have doubled from 10 to 20, 5, this one must automatically be 10. So you may be able to see the answer. But when in doubt, work it out. So I could set it up as the same as I did in the last case. Since we know these are corresponding, Ln is to Nm as Qs would have to be to Sr. So filling in what we know, 5 is to x plus 4 as 10 is to 20. And again, you may see right away that if I take half of 10, I get 5. Therefore, if I take half of 20, this denominator should equal 10. I'm going to reduce just to make it easier because it's nicer with smaller numbers. And if I cross multiply, I get 5 times 2 is the same as x plus 4. And sure enough, we end up with what we need, which is 6. So that 6 plus 4 does give us the 10 that we were expecting. Okay? So that's how we can work with similar triangles. And then in this section, there's a couple of theorems I want to go over. So we're going to first talk about what is meant by some parallel sides. Oh, goodness. I may have to get some cleaner here. My board's rolling around a little bit. So I may need to tape that down to the countertop better. Hopefully the lighting is good. Well, we just had a power outage, so I think you can still see. So I'm going to keep going. Yeah, it's looking pretty good. We'll see if the power comes back on. So here we go. If a line parallel to one side of a triangle intersects the other side, then it divides these sides into proportional segments. So if a line parallel to one side of a triangle intersects the other side, then it divides those sides into proportional segments. What I'm going to try to do is draw a picture to help visually see what we're talking about. So, for example, if I have a triangle, and again, I'm going to call it triangle ABC, and if I tell you that this segment that goes from point E to point D, if I tell you that it's parallel to side BC, then I automatically know, according to this theorem, that it divides this proportionally, meaning that line segment AE is to EB as AD is to DC. Or you could also say, if you prefer, you could look at just the left side versus the right side. You can say side AE is to the total length of AB as, you can do the same proportions on the other side. AD would therefore be proportional to the total length of AC. Or you could look at the components themselves. AE is to AD as EB is to DC. So there's all kinds of ways we can set this up based on what we are given. So let's say I give you the following, and I tell you that AE is 12 units long, and I tell you AD is 18 units long. EB is 8, DC is 12. So we can check it out. We can look at all of these. AE to EB, that would be 12 is to 8 as 18 is to 12. If I reduce the left side by 4, I get 3 halves. If I reduce the right side by 6, I get 3 halves. So sure enough, it works. But somebody else might set it up another way and say, I would like to go the short, 12 is to the total length. So 12 is to 12 plus 8 as 18 is to 18 plus 12. That would give me 12 is to 20 as 18 is to 30. If I reduce by 4, I get 3 is to 5 as, and if I reduce by 6, sure enough, I get the same proportion. Similarly, if I do 12 is to 18 as 8 is to 12, I should get the same proportion. Now, of course, I could cross multiply and see if it works. I could reduce each side by 6 and get 2/3, reduce by 4 and get 2/3, or you can always check and say, is it true that 12 times 12, 144, is the same as 8 times 18, which is 144. So there's a variety of ways to check, but this theorem is quite handy. Okay? So for example, let's take a look at a problem on this one, and we can solve it several ways. Let's say, for example, I give you the following picture. I think you can see this okay. Hopefully it's not too dark. We still have a power outage. I'm going to tell you that these two lines are parallel. And of course, this side would be a transversal. So we would still have corresponding angles which are congruent. Similarly, the other side is also a transversal. So these two angles are also corresponding, so they're actually similar, or congruent rather. Okay. So I'm going to tell you, this is not drawn to scale. I'm going to tell you that this piece is 5, this piece is 2, this piece is x, and this line segment is 4. So you have a choice as to how you want to set them up based on all the previous proportions that we did up here. Okay, so I'm going to try a couple of them just to show you. So I could say on this top side here, what I see as the top, I could set it up as the short is to the longer as what appears to be the short is to the longer side. And again, you may see it automatically by multiplying by 2. You can always use cross products. You can always go 2 times x is the same as 5 times 4. And so we end up with 10. Somebody else might prefer to go 5 is to the total distance of 7 as x is to the total distance of x plus 4. Cross multiply. So I'm left with 7x equals 5x plus 20. Subtract 5x. Divide by 2. And again, I still get 10. So there's a lot of ways you can work on these. Okay, but that's a pretty cool theorem having to do with being parallel to one of the sides. Now the next theorem I want to talk about is the mid-segment theorem. But before we do that, we need to talk about what a mid-segment is. Okay, so let's do that. Because the mid-segment theorem uses the midpoints, and we learned how to construct and find midpoints by doing a perpendicular bisector. So we could construct a midpoint and therefore use mid-segments. So let's first look at what a mid-segment is. The definition of a mid-segment. Well, the word kind of tells you that it's the middle of a segment. So it's a line segment connecting the midpoints of any two sides of a triangle. Okay? A line segment connecting the midpoints of any two sides of a triangle. And again, we can find these midpoints by constructing a perpendicular bisector and noticing that point of intersection and call that the midpoint. Okay, so what does that look like? Well, the mid segment would look something like this. Okay, doesn't have to be an equilateral triangle, it's just a triangle. If point D and point E are midpoints, then this segment DE is a midsegment. How do I know if both of these are midpoints? Well, your picture would either have to tell you that we have two congruent sides and two congruent side segments, so therefore we know it's the midpoint. Similarly, I could also say, well, let's take point F and make that the midpoint. Therefore, this line segment and this line segment are congruent, and I have now produced a midsegment from E to F. And similarly, DF is also a midsegment. So a nice activity to do is to construct and find all the midsegments of a triangle. So then we do have a midsegment theorem. Midsegment theorem of a triangle, okay? Which says the midsegments joining any two sides of a triangle is parallel to the third side and is half as long as the third side. The midsegment joining any two sides of a triangle has two things going for it, okay? Is parallel to the third side and is half as long as the third side. So, for example, let's say I give you this drawing and I tell you that this segment connects these two midpoints together. So this is congruent, these two are congruent, and I tell you that this is X, I automatically know the other side parallel to it is twice as long. Or the midsegment is half as long as the third side. So if I give you something with some numbers, just to give you the idea, here's our midsegment, which means these sides lengths are cut into two congruent pieces as well as the other two sides. If, for example, this is 7, this parallel side must be 14. So if I give you a triangle and I connect the midsegments, and I tell you this midsegment is 7, and I tell you the other length is 2x minus 3, what is x? Well, some of you will automatically go, well, it's got to be 14. It's got to be twice as long. So 2 times 7 must be the length of the third side, and therefore 14 equals 2x minus 3. Add 3. Divide by 2. This is 17 halves. Okay, so x is 17 halves, and just to check, if I substitute that back in, 2 times 17 halves minus 3, that gives me 17 minus 3, and sure enough, that entire side would be 14. Oh, I think it ran out of room. So it should be, ends up being 14. Okay. So we've now talked about some of the applications of similar triangles. Let's take a look at how do you prove triangles are similar. Okay. So just like congruence theorems, we have some theorems for similarity. So you might recognize some of the acronyms. All right, so let's prove triangles are similar. And we have 3 ways of doing that. To prove triangles are similar, we have 3 different similarity theorems. We have side, side, side. We have side, angle, side. And we have angle, angle, triangle similarity. So let's take a look at each one. The first one, side, side, side similarity. Side, 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 triangle similarity. Is, no pun intended, similar to congruence. However, we're not talking about congruent segments. We're talking about sides being proportional. So if the length of corresponding sides of 2 triangles are proportional, then the triangles are similar. Okay. If the lengths of corresponding sides of 2 triangles are proportional this time. Since we're talking about similarity, then the triangles are similar. Okay. So for example, if I have triangle ABC, and I have which has side lengths AB of 3, BC of 9, and AC of 5, we want to try to prove that it is similar to triangle DEF, where side DE is 6, side EF is 18, and side DF is 10. So in order to show this with side, 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 we must show that all 3 sides are proportional. So let's set up our proportional sides again, our corresponding sides. Side AB is to DE, as they're sitting in corresponding location, as BC is to EF. We have to show all 3 sides, so we need to also list side AC would correspond to DF. And we need to double check to make sure all 3 fractions, all three ratios are the same. So in this case, I would then just prove this by saying, okay, AB is 3, DE is 6. Is that ratio the same as 9 to 18? And is that ratio the same as 5 to 10? By reducing each set of fractions, we get 1/2 is the same as 1/2 is the same as 1/2. So we would therefore say triangle ABC is similar to triangle DEF by side-side similarity. So we must show all three sides are the same ratio, therefore they're proportional. All right. Power hasn't come back on yet, so hopefully you can still see this well. All right. And we'll keep going until the battery dies on the computer, which I think it'll make it through. Let's take a look at our next form of similar triangles. Didn't mean to erase it. Hopefully you remember the second one we're looking at is side angle side triangle similarity. And of course the order kind of tells it away. We need the angle to be between the two sides that are proportional. So if two sides of one triangle are proportional to their corresponding sides of another, if two sides of a triangle are proportional to their corresponding sides of another triangle, proportional to their corresponding sides of another triangle. Now, we've talked about the two sides. We need to also remember that they've got an included angle, and for similarity, the angles must be congruent. So, and their included angle and they must be congruent, have the same measure, then the triangles are similar. So once again, we said our corresponding sides are proportional, and we said their angles are congruent. That's why we're proving similarity. So, for example, let's say I give you this right triangle, and we'll call this triangle ABC, where C is the right angle, and triangle DEF, where F is the right angle. I would like you to show that these two triangles are indeed similar. So in order to do that, well, we would start off with what we know, and so we need to check, let's say, let's look at their corresponding sides. AC is to BC as corresponding sides, DF is to FE. So we could say 4 is to 5 as 12 is to 15. Reduced by 3, we end up with 4/5 is to 4/5. So that works. But we also, now that we know their sides are proportional, we also have to show that the angle is congruent. and the measure of angle C is the same as the measure of angle F, they're both 90 degrees, we can say therefore that angle C is congruent to angle F. So now both situations are satisfied. Therefore, we can say, therefore, triangle of dots, triangle ABC is indeed similar to triangle DEF by side angle side similarity. Okay, so hopefully that helps clarify that theorem. And then for this section, we only have one more theorem. So we'll take a look at that, and then hopefully this will help. All right, so our last triangle similarity theorem is angle-angle similarity. And what's interesting is we only need two of the angles, because we know the sum of the angles in a triangle is 180. So if two of them are congruent, the third one automatically will be congruent as their sums would be the same. So if we have angle-angle similarity for triangles, if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. If two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. Then, how about just then? The triangles are similar. So let's say I gave you this triangle. I'll call this triangle ABC. And I tell you triangle A is 60 degrees and triangle B is 50 degrees. Well, if we have another triangle, we'll call this triangle DEF, and triangle D happens to be 60 degrees as well, and E happens to be 50 degrees, then the third angles would have to be the same, since the sum is always 180 degrees, and we can say, since the measure of angle A is the same as the measure of angle D, this means that angle A is congruent to angle D, and since the measure of angle B equals the measure of angle E, by definition, this means angle B is congruent to angle E, then triangle ABC is similar to triangle DEF by angle-angle similarity. So hopefully that helps with section 12.4, and we can move on to the next section at another time.